Hello. Last week, we went over molar conversions and we were using only the left side of the mole map. But this week, we are going to be starting stoichiometry, that word that I said in class that most of you were like, what the heck? But yes, we're going to be starting stoichiometry, and that's going to use the entirety of the mole map. And basically what it is it's taking conversions and it's cranking it up to the max. So we're talking 1, 2, 3, sometimes 4-step conversions, depending on what you would like to do. So what even is stoichiometry? What is that weird word? What does it mean? It describes the numerical relationships in chemistry. It is based on the mole. It's based on that 6.022 times 10 to the 23rd power. And lucky for you guys, it's always going to be a whole number ratio between reactants and products, between reactants and other reactants, between products and products, between a lot of things. But there are two main types of stoichiometry that we can use. The first one is called composition stoichiometry, and that is going to be the numerical relationship between elements inside chemical compounds. So we've talked about this a little bit peripherally, but basically what that means is, take a water molecule, for example. For every 1 oxygen, there are 2 hydrogens. So we can say that there is a 2-to-1 molar ratio of hydrogen atoms to oxygen atoms, because there's 2 hydrogens for every 1 oxygen. Okay, and again, we've talked about this a little bit when I asked you in a formula like H2O, oh, how many hydrogens are there? How many oxygens are there? So you know this a little bit. This, however, is not the particular part of stoichiometry that we're going to be focusing on. We are going to be focusing on reaction stoichiometry, which is about molar ratios between reactants and products in a chemical reaction. Okay? So let's take the synthesis of water, for example. Let's stay with water. Oops, let me go back. In that particular reaction, we have hydrogen and oxygen gas are going to react together and they're going to form water. But when we balance that equation, we had to put coefficients in front of hydrogen and in front of water. So in front of every single reactant and every single product, there is going to be a number. Now, some of you might be going, but Miss Seiler, there's no number in front of oxygen. No, but when there's not a number, it's just like there's a number 1 there. So that blank space is an implied 1, just like before, wow, there's an implied 1 right there as well. Okay, so these numbers, this 2 in front of hydrogen gas, this 1 in front of oxygen gas, and this 2 in front of water are very important, because not only does this mean it takes 2 molecules of hydrogen and 1 molecule of oxygen to produce 2 molecules of water, we can scale that up a little bit. So this 2, 1, 2 is actually molar amounts as well. So you can react 2 moles of hydrogen with 1 mole of oxygen and produce 2 moles of water out of that, which, if you really think about it and you sit down and you consider that for a second, it makes sense, because we're not doing reactions on molecular level. No scientist is going, okay, I'm going to isolate exactly 2 molecules of hydrogen and exactly 1 molecule of oxygen and do that reaction. No, we're doing that on a large scale. We take some hydrogen gas and some oxygen gas and produce some water out of it if we were to do that reaction. So everything is basically in a large scale. Okay. So once again, we have a molar ratio happening between amounts in moles of any 2 compounds in a particular reaction. We are going to use that molar ratio as a conversion factor to do calculations. So if I start with some amount of reactant, I can figure out how much product I'm going to get. Okay, so we're going to use the coefficients to represent the number of moles. So if I wanted to know the ratio of nitrogen to ammonia, you would tell me that that is a 1:2 relationship because I have 1 mole of nitrogen for every 2 moles of ammonia. If I wanted to know the ratio of hydrogen gas to ammonia, you would tell me that that is a 3:2 relationship because for every 3 moles of hydrogen gas used, 2 moles of ammonia are produced. You could even do this backwards, you guys. I might ask you, okay, well, what's the ratio of ammonia to hydrogen? In which case you would tell me 2:3. I might ask, what's the ratio of hydrogen to nitrogen? And you would tell me 3:1. That is how easy figuring out that molar ratio is, okay? But we're going to use that to do other calculations. And that is going to involve your mole map once again. So on your mole map currently, you probably have this part circled, okay? But now we're not only going to use that part, we're going to use the entire thing. And to move from over here on the left, which you already know how to do, and to move towards the right, you need this little n here, this little n. And that is called your molar ratio. And you see this little fraction up here. Your molar ratio is moles of what you need divided by moles of where you started. So quite literally, in a reaction scenario, whatever you want, whatever the problem wants, you're going to say moles of that over the moles of whatever your given number is. And I know that probably sounds a little bit confusing, but we're going to do a lot of practice problems for you guys to figure that out. So let's do a sample problem, because the easiest way to explain something is to do a sample problem. So our sample problem says, I have 10 grams of iron. How many moles of iron 3 oxide can I make? Okay. And you want to, 1, have an equation to start with, first and foremost. And 2, you have to figure out what the problem is asking you for and what your problem wants out of it. Okay, so boom, there's my equation, and let's analyze this question really quickly. Okay, this question says, I have 10 grams of iron. So right away, you should know that that is your given number right there. That 10 grams of iron is your given number. The problem is asking for how many moles of iron 3 oxide. So 1, it requires you to know what the question is asking for, and 2, you have to know what iron 3 oxide even is, okay? So let's take a look first at this equation down here. So this is a skeleton equation. It is unbalanced, as you can probably tell. So we have iron and we have oxygen gas reacting to form iron 3 oxide, okay? So the first step in being able to do this conversion at all is balancing your equation. So we're gonna go from left to right, and we're gonna do that. We have 1 iron over here, we have 2 over there, so right away we know we should probably be putting a 2 in there. We have 2 oxygens here and 3 over there. So if you recall my tips and tricks, as soon as you see an even-odd situation, you try to make your odd one even by multiplying by 2. So if we throw a 2 in front of that, that takes care of that. But we have to go back and we have to change this coefficient. Now that we have 2 times 2 is 4 irons over there, we would have to put a 4 right there. And if we have 6 oxygens on our right, we have to put a 3 in front of that oxygen there. So now we have a balanced equation. We have something that we can work with, okay? Then we have to actually go ahead and look at our mole map and figure out what kind of conversion we have to do, because we know what our given number is, we know it's 10 grams, and we know I want moles. So we're starting with a gram amount, a mass, and we're going towards moles of something, right? We're not going for moles of iron, we're going for moles of iron 3 oxide. So the procedure on the mole map is going to change just a little bit. So once again, I'm going to rewrite some stuff. We're starting with 10 grams of iron. We want to know moles of iron 3 oxide. Okay, so that was Fe2O3. So that's what we want. What we have, this is what we want. Now, to know what conversions we have to do, we have to look at our mole map a little bit. So we're starting with, we have a mass. So we're starting over here on the left side with mass. We are going towards moles of something else. So we're not going from mass of one thing to moles of the same thing. We're actually going from mass of one thing to moles of something else. So we're actually going over here, okay, to moles of B. How do I know it's not moles of A? Because if it was moles of A, it would ask me for moles of iron, but it's not. It's asking me for moles of iron 3 oxide. So once again, starting here, we're ending over here. So I have to go from mass of iron to moles of iron, and from moles of iron to moles of iron 3 oxide. So I'm doing 2 conversions total, 2. Okay, so we handled that skeleton equation already. We handled what that is. We have that written down. Step 2, decide what conversions we have to do. We just did that. We looked at our mole map. We're going from mass or grams of iron to moles of iron to moles of iron 3 oxide. Okay? Then, step 3, we have to set up our skeleton conversions. So we're going to draw a T-chart once again, but instead of just a T-chart that looks like this, we're going to set up a 2-part T-chart, okay? It's going to look like this. We are still going to put our given number in the upper left-hand corner, okay? So once again, this is our given number. That still goes in the upper left. So we're going to write 10 grams of iron. Yes, your units are important. You're going to put your placeholder 1 right there. Okay? Then you are going to go ahead and figure out how to write down your first conversion. So for those of you that forgot, we were going from grams of iron to moles of iron. And then from moles of iron, we were going to moles of iron 3 oxide. Okay. So first things first, we are going to do this part. Okay. So we have grams of iron here. So grams of iron has to go down there because we're getting rid of it. The first conversion we're doing is we're going for moles of iron. So that's going to go there. Okay. Then from there, we are going to moles of Fe2O3. So ultimately, moles of Fe2O3 needs to go on the top. And once again, we're going to convert out of moles of iron. So that's going to go down there as well. Okay. Hopefully you're still with me. After you have written down your skeleton conversion, and that is without a bunch of numbers in it, you then have to go and figure out what your numbers are, okay? So to go and fill in our first conversion, our grams to moles, you should already know how to do that because you have to look for molar mass. If we look at our mole map, I told you that if we're converting from grams to moles, we're dividing by our molar mass of iron. So if we look on our periodic table, we find that the molar mass of iron, for every 1 mole of iron, it is 55.847 grams. And since we're dividing by our molar mass, we know that that big number has to go on the bottom. Okay? Now, to fill in the numbers here, if you recall from the other slide, it's moles of what you want over moles of what you have. So what we want is the number of moles of iron 3 oxide. So we look at our equation and we say, oh, there's a number 2 next to iron 3 oxide. So for every 2 moles of iron 3 oxide, we are using 4 moles of iron. And that is how you get your molar ratio. That moles of what you want over moles of what you have, that comes from your equation. So don't ever think that that number is going to come from anywhere else. That's what the balanced equation is for. Your next step is going to be to cancel out your units, multiply straight across, and then divide by whatever's on the bottom, just like we always have. So let's make sure really quickly that our units are canceling out, all right? So the first thing we're trying to get rid of is this grams of iron on the left. That's going to cancel out with this grams of iron down here. The second thing we have to get rid of is this moles of iron here. That's going to cancel out with the moles of iron down there. The only unit that doesn't cancel out is going to be this one, which is what we want, okay? So we multiply straight across on the top. We're going to do 10 times 1 times 2, which is going to give us 20 on the top. And then we're going to do this 55.847 times 4, again multiplying straight across on the bottom. And that is going to give us 223.388 on the bottom. And then we divide and we solve. So once we divide 20 by 223.388, we're going to get 0.0895, blah, 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 blah. Okay? So that's not it though. We're not quite done because we need to figure out how many sig figs we can have in our answer. So technically, yes, this is how many moles of iron 3 oxide we would end up with. However, sig figs are a thing, so we have to go and we have to look at this number here. And if you look at it, the number 10 has 1 sig fig in it because there's no decimal point right there. Otherwise, it would be 2. So we're going to have to round this number down here to 1 sig fig. So how are we going to do that? We are going to go ahead and round this off, okay? So we can round to this place, the hundreds place right there. So we're going to round that off, and since the next number over right here is a 9, it's going to round to 0.09 moles of iron, 3 oxide, okay? And then this is going to be your final answer. Once again, if that was confusing to you, we're going to do a couple of other practices. So don't panic, okay? After you've done that, you're going to check your work real quick. I started out with 10 grams of iron. Is that more or less than 1 mole? To figure that out, all you have to do is look at the molar mass. If the molar mass is more than the mass you started with, yes, that's less than 1 mole. So if I got less than 1 for my number of moles, I should be on the right track. If you got a crazy number like 45 moles, you probably did something wrong. So there is specific types of conversions. Whoops, went too far ahead. The first type is going to be a mole to mole conversion, okay? And when we are in class, I'm going to give you some quick formulas so that you don't have to stare at your mole map and wonder what conversions you're doing all the time. It's going to be really, really easy. But again, I'm going to give those to you in class. For now, we're going to look at the mole map. So I certainly hope that you have your mole map out. Okay, so we have a question. Potassium mixes with water to produce potassium hydroxide and hydrogen gas. Given that you have 0.0400 moles of potassium, how many moles of hydrogen is produced? Okay, so firstly, we have to write out an equation. So we have potassium, and that is going to mix with water, and it's going to produce potassium hydroxide and hydrogen gas. Remember, hydrogen gas is a diatomic element, so that's going to show up in a pair. Next step is to balance. So let's make sure that I have equal amounts of stuff on both sides. We have 1 potassium on the left. We have 1 potassium on the right. So far we're good to go. We have 2 hydrogens on the left, and we have 1, 2, 3 on the right. So that's a problem. So right away, I'm going to try to make my odd and even. So I'm going to throw a 2 in front of there and see what that does. That's going to change my potassium over here, necessitating a 2 right there. Now I have 2 hydrogens on the left and a total of 4 on the right. So I'm going to throw a 2 in front of here to make that 4 on the left. That gives me 2 oxygens on the left and 2 on the right. So I am all balanced now. Okay, cool. I have a balanced equation. Then I want to look at my mole map to figure out what the heck kind of conversion I'm actually doing. If I look at what the problem gives me and what it is asking for, it's asking me, hey, guess what? I have this many moles. How many moles is produced? So that's why we're doing a mole to mole conversion. Moles of A to moles of B. A is going to be your given number. B is what the problem is asking for. So these ones are going to be one-step conversions. So these ones are easiest. As usual, we're going to put our given number in the upper left. 0.0400 moles of K. Placeholder 1. Moles of B over moles of A. Moles of what you want over moles of what you have. So moles of H2 over moles of K. Once again, this mole ratio is going to come directly from your equation. So here, we're looking for this number, and we're looking for this number. Now this one is blank, so that's going to be for every 1 mole of hydrogen, we are using 2 moles of potassium, okay? And then we're going to multiply straight across on the top, multiply straight across on the bottom. So we're going to get 0.0400 on the top. We're going to get 2 on the bottom. And once we divide, that's going to be 0.02 moles of H2. How do I know what unit I'm in? Well, because that unit is going to cancel out with that unit. And the last thing is to check our sig figs. Now, this has 1, 2, 3 sig figs. So these 3 digits right here are significant. So this is going to need to have that many sig figs. So we're going to say 0.0200 moles of H2 as our final answer. Next, we are going to have a mole to mass conversion. So we're going to go from moles of A to mass of B, okay? So once again, step 1, figure out what the problem's asking you for and write a balanced equation. So let's take a look. Determine the mass of sodium chloride produced when 1.25 moles of chlorine reacts with sodium. So this one's said a little bit backwards. We know that sodium chloride is going to be produced because the problem tells us. We also know that sodium is going to react with chlorine. Chlorine it tells us is Cl2, even though we could have figured that out because it is a diatomic element, and that is our skeleton equation. Now we have to balance it. 1 Na over on the left, 1 Na on the right, so that's good. 2 chlorines on the left, which means we need a 2 there, and we need a 2 there. Now we are balanced, and we're good to set up our conversion. So mole to mass conversions are going to be two-steppers. So we are going to set up a two-step T-chart. Once again, our given number that the problem is giving us is going to go in the upper left-hand corner. And in that case, it's our 1.25 moles of chlorine. So we write that there. We write our placeholder 1 right down below. We want to know the mass of NaCl. So all the way over on the right, grams of NaCl should be right there. Okay, so now we look at our mole map. We figure out what the heck we're even going to do. By looking at the mole map, you're going to need to figure out are going to go from moles, let me write this up here, moles of Cl2 to moles of NaCl to mass of NaCl. If you are confused as to where I got that, I will be happy to show you in class. Okay, so our first conversion, moles of Cl2 to moles of NaCl. So that's this portion of our T-chart. So moles of NaCl needs to go right there. We're getting rid of moles of Cl2, so it's going to go right there. And the second part of this conversion that we're going to do is going to be from here to here. So to convert out of moles of NaCl, we need to put it down here as well, moles of NaCl. And now we can fill in some numbers. Okay. So this mole over mole, that's going to be our mole ratio, and that's going to come from our balanced equation. Our number next to NaCl is 8.2. Our number next to Cl2 is not there, so it's going to be a 1. And then to go from mole to mass, we are going to need a molar mass. So for every 1 mole of NaCl, we are going to have a certain amount of grams. And if you recall, we find that on the periodic table. You're going to add the mass of sodium to the mass of chlorine. Once you add that up on the periodic table, the mass of sodium is 22.99 grams. The mass of chlorine is 35.45. Added together, that is going to be 58.44 grams. Now, once again, we multiply straight across on the top. We multiply straight across on the bottom. Everything on the bottom is 1 times 1 times 1, so that's going to give you a 1. We're going to do some multiplying on the top. So let's do 58.44 times 2 times 1.25, and that's going to give us 146.1. Now we're going to cancel our units. Moles is going to cancel moles. This moles is going to cancel that moles. We are left with grams. 146.1 grams of NaCl. Now, is that proper sig figs? No, because 1.25 has 3 sig figs, so this can only have 3 sig figs. So we're going to round that off to 146 grams of NaCl. Type 3 is going to be a mass-to-mass conversion. These are the most complicated ones because these are going to be your 3-steppers. Now, we're going to start this off the exact same way. We are going to look at what the problem is asking us for. We're going to write a balanced equation. This says ammonium nitrate produces dinitrogen monoxide gas and water when it decomposes. Determine the mass of water produced when 25.0 grams of ammonium nitrate is decomposed. So this is actually really nice. It tells you the chemical formula for ammonium nitrate. So let's fill that in down here. NH4NO3. Now we were told that that's decomposing, which means that there's only one reactant, And we were also told what it decomposes into: dinitrogen monoxide gas and water. So now we have our skeleton equation. We're going to balance it real quick. So let's see. We have 2 nitrogens over on the left. We have 2 on the right. We have 4 hydrogens over on the left. We only have 2 on the right, so we're going to put a 2 right there. We have 3 oxygens on the left. We have 1, 2, 3 now over on the right, so that is actually it. We don't have to do anything else. And now we are going to look at our mole map. So we were given a mass. We were given 25 grams of our first thing, of A. And I want to know the mass of water. That's our B. So when we do that, we have to go from mass of NH4NO3 to moles of NH4NO3 to moles of water to mass of water to get all the way over to where it wants us to be. Now, this is going to be your 3-step conversion. So let's draw out our T-chart. It's going to be a little bit bigger. 1, 2, 3. Put our big line right there. As usual, your given number, this guy right here, is going to go in your upper left. So that's your 25.0 grams of NH4NO3. Our placeholder 1 is going to go right there. All the way over on the other side, grams of H2O is going to go because that's what we want. Now, our first conversion is to go from grams of NH4NO3 to moles of NH4NO3. And I know that's kind of smushed. So to do that, we have to get rid of the grams. So the grams of NH4NO3 is going to go right there. To get from moles of NH4NO3 to moles of water, we have to do that molar ratio thing. So our moles of NH4NO3 is going to go on the bottom. Moles of water is going to go on the top. So that was this conversion right here. And then lastly, we're going from moles of water to grams of water. So if we want to get rid of moles, moles needs to go down there. Whoops, stopped drawing. And we already wrote in grams of water on the top. So now we can start filling in some numbers. So we're going to say, okay, for every 1 mole of NH4NO3, what gram amount is that? Assuming you look on your periodic table, you're going to add up your 2 nitrogens, your 4 hydrogens, and your 3 oxygens to come up with a mass of 80.0426 grams. Okay, so that's your molar mass of NH4NO3. Then in this middle step, it's moles over moles. So we're going to go moles of what we want over moles of what we have. Next to moles of H2O, there's this nice 2 in our equation. So for every 2 moles of water that's produced, we use that blank implied 1 mole of NH4NO3. Then to do our last step of the conversion, for every 1 mole of water, there are a certain amount of grams of water. So you take that 15.999 grams of oxygen and add it to 2 of your 1.0079 hydrogen. So when I do that on the calculator, I get 18.0148 grams of water. Now, that was a little bit long, but we're still going to do the exact same thing. We are going to multiply straight across on the top, multiply straight across on the bottom to end up with this big fraction over here. So we're going to do 25.0 times 2 times 18.0148 0.0148, and that's going to give us this number. Oops, 0.74. And then on the bottom, we're going to do 1 times 80.0426 times 1 times 1. So that is quite literally going to say the exact same number. And we are going to divide those two, that 900.74 divided by 80.0426. And that is going to give us 11.3. So remember, this is in grams, and it is in grams of water. Why did I round it off to 3? Because the original given number had 3 sig figs in it. So that was a big long problem, but we just converted from mass of what we started with to mass of what we are ending with. Now, I am very, very sure that some of you are sitting there going, oh my God, how am I ever going to do these calculations on my own? And I know that you're sitting there like that because I sat there in my chemistry class in high school and felt the exact same way. It was like, oh my God, I don't understand this. How will I ever get it? And then I practiced it. And then one day I was just like, oh my God, I understand this now. And it will be the same exact way for you. You're going to not get it and not get it and not get it. And then it's going to click for you. And it will become one of the easier things you will do in this class. Trust me, I know I have been there. So I hope that this was somewhat helpful. Again, I will be giving you some more notes and things to deal with in class.